Isomerization can play a really important role in some biologically interesting molecules. It can mean the difference between a drug and a poison, or can play a role in a molecule catching a photon of light and sending a signal to our optical nerves that we just saw something. So here's this molecule, all-trans retinal, which we do use in a protein to help as an antenna for photons of light, and we want to know how is it related to these other two molecules, vitamin A1 and 11-cis retinol. So first off, we can just start comparing carbons. This is kind of a college level spot the differences game. We got this ring with a single double bond in it and 3 methyl groups coming off in particular locations. Looks the same as this here, even though here the methyl groups are made explicit. It's the same as here, but rotated a little bit. Okay, off from that ring, we've got this carbon chain that's 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons long. Well, it's the same here. 2, 4, 6, 8, 9 carbons long. 2, 4, 6, 8, 9 carbons long. It has 2 methyl groups coming off of it. If we're counting, well, we should count from our priority group here after the first double bond and the third double bond. So methyl group after first and third. Here, after first, there's a methyl group. And after the third, there's a methyl group. So these have all the same carbons. Here we've got an aldehyde. I could draw it like this to make it all explicit. Here we have an alcohol, and up here we have an alcohol. So we know right off that with all the carbons the same number of oxygen, each has only 1 oxygen, we know that this molecule is not an isomer or a stereoisomer or the same as these other two, because these two have 2 extra H's. If I put that C in, this C has 2 H's, as does this C. So while it's a very similar molecule, it is an oxidized form of vitamin A. But these two not only have all the same carbons, they have the same oxygen functional group, alcohol in both cases. So these could be the same molecule, except if we look at our double bonds and draw a line through them, and then do the same here, down here, from this double bond, we go to the left and to the right. This is a trans double bond. This one again, a trans double bond. The biggest groups are across from each other. This vitamin A1 is all trans, just like all trans retinal. Now here with this 11-cis retinol, we've got trans on this double bond, trans on this double bond, but this the biggest groups, the hydrogen, the smallest groups are on the same side, and the big groups are on the same side across here. So this is a cis double bond at this point. So these two are stereoisomers. So that's a process you can follow. Check all the atoms, check all the functional groups, line them up even if they're in different representations to figure out if things have the same atoms and could be isomers, and then see how they're attached together. Here, vitamin A1 and 11-cis-retinol, all the atoms are attached in the same order, but the stereochemistry changes at one of the double bonds. So those are things that you can look for as you try to find isomers and stereoisomers in larger molecules.